In lecture 18 of Symmetries, Particles and Fields, we're going to develop our discussion of representations of simple, compact Lie algebras. And then we're going to give some pertinent examples in terms of SE3. These will come in handy later in the next chapter where we discussed hadrons. And more generally, SE3 and representations of SE3 are useful in particle physics in terms of the construction of the standard model. Okay, so we're going to now give some helpful definitions, and these are about the root and weight lattices. So if you remember last time, we have some set SD of weights of some particular representation, little d. And we derived that this in a product between alpha, between the roots, or a particular root, and the weight in this combination is an integer. So that's going to be, and we know that from our knowledge of basically what happens with the Lie algebra of SE2 representations. So let's make some definitions. So a root lattice, which of a Lie algebra, we're going to write as curly L of the Lie algebra. This is just the span of the roots, the simple roots actually, span of the integers of the roots. Okay, which of course is the same as the span of the integers of the simple roots. And then we have normalized roots, which are called simple co-roots. So these are written with a caron. Okay, that's a definition. This is definition. And this is just a simple root times 2 over the length of the simple root squared. Okay, then we have what's known as a co-root lattice. And it's pretty easy to guess what this is going to be. So we write this as curly L caron of L of G. So this is the span over the integers of our simple co-roots. And this co-root lattice has a dual, which is called the weight lattice. This is written as LW for weights of L of G. And this, of course, is the dual of the co-root lattice. So we write the dual with an asterisk. I can write the asterisk actually there. That's what I've done later. So this is defined to be So we take lambda in the, well, lambda is a weight basically, so it's in the dual to the Cartan subalgebra, such that lambda and mu is an integer for all mu in the co-root lattice. I'm sorry, I got the caron the wrong way around. It should be upside. It's an inverted hat, a caron. Okay. So these are basically, these lambda correspond to our weights, and they're going to satisfy this equation here, where, so now if you substitute in for mu that I've just given you, you'll see that we get this combination, and so it has to be an integer. So in particular, lambda is in our weight lattice if and only if lambda with alpha I caron, the co-root, the ith co-root, is twice alpha I lambda over alpha I, no sum on I. So we showed in the last lecture that this is, well, we said that this was equal to an integer from our knowledge of SU2 or representations of the SU2 Lie algebra. So the weights of any representation lie in this weight lattice. So any representation D of the Lie algebra lie in the weight lattice of the Lie algebra. And the simple co-roots are a basis for the co-root lattice. So we have a dual basis for the weight lattice. So I'm going to call this dual basis the set of all Wi's. Okay, because this gives you an integer, these weights are just defined so that a co-root in a product with this weight is twice alpha I weight j over alpha I, no sum again, I is equal to delta ij. Okay, so that's going to give us a dual basis for the weight lattice. So these Wi are important. They're called the fundamental weights of the Lie algebra. So the simple roots, of course, span our dual space to the Cartan subalgebra. So then we can write that these Wi just must be some linear combination of the simple roots. And that linear combination, I'm going to write it in a matrix form. So B is a matrix, real matrix. It's R by R, of course, and Bij of the elements. So 6.9, if we take the middle term in 6.9, we just substitute in for Wj, we get that 2Bjk alpha I comma alpha k over the inner product of alpha I with itself, okay, well, is equal to delta ij. But what we notice is that the factor multiplying bjk, which with the sum over k now is equal to the kith element of the Cartan matrix. Okay, so if we look at this equation above, then what we see is that our matrix B is the inverse of the matrix, the Cartan matrix. In other words, alpha I is Aij Wj. Okay, so let's go back to our example of SU3. We know what the roots are, and we can write these now in terms of the fundamental weights using this equation. So the algebra of SU3. So our Cartan matrix we've seen before is this one. And so we have that alpha 1 is twice W1 minus W2, and alpha 2, just reading off from the matrix, is minus W1 plus 2W2. Okay, so these are two linear simultaneous equations, easy to solve. So we can write the weights in terms of the roots. By the way, alpha 2, previously we called this beta. We called these alpha and beta before, these two roots of SU3. But in order to generalize it, I've called them alpha 1 to alpha n, or to alpha r, I should say. So to alpha plus beta, and W2 is a third alpha plus 2 beta. So if we draw if this is alpha 1 and that was alpha 2, they have the same length, remember, and there's 2 pi by 3 between them, then this is W2 and this is W1. Okay, so these fundamental weights are a basis for any weight in the weight lattice, for the weight lattice. So any weight within the set of weights so this has to be in the weight lattice of our Lie algebra. So this can be written as a linear combination of these fundamental weights. That's what being a basis is. So we can write that lambda is lambda I times wi, where now these lambda i's are integers. To move these movers around the lattice, and these are the Dynkin indices. Or they label different elements of the lattice. So the Dynkin indices of the weights. So every finite dimensional representation must have a highest weight such that we can't raise it. So every finite dimensional representation D of L of G must have a highest weight. So we're going to call this lambda such that d e alpha acting on V is 0 for all positive roots. And for all V in the vector in the irrep space, in the representation space of this representation. Now, there is this theorem called the theorem of the highest weight. There are going to be a few theorems which crop up, or a couple of theorems and lemmas which we can't prove now. Some of them are quite involved and involve, you know, learning about other things like Verma modules to prove, and we don't have time to do that. So I'm going to just do is quote you a result from, it's one of the results from the theorem of the highest weight. And one of the things that this states is that if d lambda is a finite dimensional irreducible representation, if and only if the highest weight lambda is unique, it exists, it's unique, and it has multiplicity 1. Multiplicities are of weights in representations are tricky to find in general. One can find kind of iterative equations for them. There's this Freudenthal construction. Again, it's a whole, you know, it's a whole long thing to prove it, and we're not going to go into that. Okay, so the theorem of the highest weight actually tells us some other things too. It tells us that if you find the highest weight of any representation, and it's equal to the highest weight of another representation, then the two representations are isomorphic. So the highest weight is a good way of labeling representations. So anyway, we've got this highest weight state, and we find the rest of the states by acting with lowering operators. So these are representations of E minus alpha I when alpha I are still in the positive root set. And we act on this highest weight state. So in other words, the lambda is d e to the minus alpha we act with several of these, k of them, say. So every weight can be written of the representation. So I'm going to call this representation D. I'm going to label it by the highest weight. This can be written as lambda is the highest weight minus mu, where mu now is sum I equals 1 to r, some natural numbers times alpha I. So mu I, natural numbers, they can be 0. That's essentially what the above equation is saying. All right, so, there's sometimes people call the highest weight the dominant weight. Highest weight is more common in physics applications. All right, now we have another result, which is going to be useful the proof omitted. It's a long proof. It's useful, and it's a lemma. So for any finite dimensional representation, of the Lie algebra, if lambda is some expansion of the weights, if lambda is basically in one of the weights of the representation, then lambda minus mi alpha I, no sum on I, this is also in the weight space. So now mi is a natural number and mi is less than or equal to lambda I. Okay, so this lemma is going to help us construct some representations. In fact, we're going to go back to SU3, to the algebra of SU3, and watch this lemma in action. I'm going to return to SU3 a few times. So let's look at the fundamental representation. So we call it F. This has Dynkin indices F for fundamental, Dynkin indices. So lambda 1, lambda 2. Okay. I think I'll use this. So I think I've used it with indices upstairs, didn't I? Lambda 1 and lambda 2. So this is 1, 0. Okay, so what this means is that lambda is, if we're just expanding it in this way, lambda is just the first fundamental weight, and this is in the rep space of the highest weight of the fundamental rep. So it's in the rep, yeah, it's in the weight space of the fundamental rep. So now our lemma tells us that we can lower by alpha 1 once. So in other words, we take lambda minus alpha 1, which is, so remember we derived what alpha 1 and alpha 2 were in terms of the weights. We just solved this equation here, and we got alpha 1 and alpha 2 in terms of the weights given by the Cartan matrix. So alpha 1 is equal to 2w1 minus w2. Okay, so this is just equal to w2 minus w1. So again, this is in the weight space of the fundamental rep, and I'll use our lemma again. So again, we have that we have a positive coefficient for w2. Then we can lower this with alpha 2. So we take alpha 2 off this, so w2 minus w1 minus alpha 2. And if you do that, you'll get minus w2, and this is also in the fundamental rep. And then we can go no further because we have no positive coefficients multiplying the fundamental weights. So we see that we have a three-dimensional representation. There are three states: lambda, lambda minus alpha 1, and lambda minus alpha 1 minus alpha 2. So the weight diagram is the following. We draw the two elements of the Cartan subalgebra, H1 and H2. We start with lambda, which is up here. We took lambda minus alpha 1, and then we took lambda minus alpha 1 minus alpha 2. I should say. minus alpha 1 minus alpha 2. Okay, so here's the different weights of this fundamental rep. So it's three-dimensional. So in a field theory, what we're going to do is use the representation space for the different fields. So this is a complex field. Let's call it phi, with three components. So in other words, SF, we're going to look like phi 1, phi 2, and phi 3. We've written this before as phi I, where I is 1, 2, or 3. And we've also written it as a 3. Okay, so there's a little simple exercise to apply this yourselves. So find the weights for a different highest weight state. 0, 1. And this is actually, it turns out, this is 3 bar. So if you do this, you should do it yourselves, but you should find the following. So the highest weight lambda is, it turns out, is here. And then this is minus alpha 2, and then we get minus alpha 1. Now, we can see that we get the same weight diagram by taking the original one of the fundamental representation and reversing the axes. So actually, this is a more general property. Okay, there are several things that we can say about this. That actually, so again, we're going to pull a result out of the hat and not prove it. So for highest weight, lambda 1 and lambda 2, it can be shown with some pain, which we're not feeling hard enough for today, that the dimension of the representation labeled by lambda 1, lambda 2 is a half lambda 1. This is only for SU3. Half lambda 1 plus 1, lambda 2 plus 1, lambda 1 plus lambda 2 plus 2. And also that the dimension, that d of lambda 1 comma lambda 2 is the conjugate of the lambda 2 comma lambda 1 representation. So we can also show that lambda is in the weight space of lambda 1 comma lambda 2 implies that minus lambda is in the weight space where we change the highest weights over. Okay, so another thing we notice between these two things is that if we, that's exactly what I said before. If we reverse the axes, in other words, we take H2 to minus H2 and H1 to minus H1, we end up with the this other diagram, and this is borne out by this third point here. All right, now there's one other exercise which you can do. It doesn't take too long. That's exercise 1. Exercise 2. Find the weights. So you can use these facts, but find the weights for highest weight is 1, 1. There are 2 zero weights. In other words, the multiplicity of the zero weight is 2. Okay, and what you should answer from that exercise using the lemma is the following. So there's our highest weight, and we should get a diagram like this. So I've put 2 dots in the center to denote multiplicity 2, zero weight. So this is the 8-dimensional representation. Now, we notice that if we reverse the axes H1 and H2, so we reverse the weights, then we get the same thing back. So this is a real representation. So we've seen a diagram very much like this. The one which is the same but without the zero weights is the root system. So it's the same as the root system plus R zero weights. So this is the adjoint representation of the Lie algebra of SU3. Okay, good. Now, let's talk about tensor products of representations. Let's take 2 representations of the group. So di of G, where I is in 1 and 2, is either 1 or 2, with associated representations of the Lie algebra. And representation spaces VI. With weights, okay, lambda I. So in other words, we have that di of Hj acting on Vi is lambda Ji acting on Vi. All right, so now consider a general element of the Cartan subalgebra. So this is some xi times hi's, and we put g is the exponential of hx. All right, so now let's apply our rules for the tensor product to this case. D1 cross O times D2 corresponding to HX. Acting on the representation space, the tensor product is, so we get D1 acting on the first vector cross V2 plus V1 cross D2 acting on the second vector. All right, so we know what each of these things is from the above. So this is equal to xi d1 hi v1 cross v2 plus v1 cross xi d2 hi v2. And we know from the equation above what each of these products is in the brackets, in the parenthesis. So this is xi lambda I1 plus lambda I2 on v1 cross v2. So what we see is that in a tensor product, the weights add. Between two representations, the weights add. So what does this mean? So for example, let's go back to our Lie algebra of SU3 case. H1, H2. Okay, so let's take a 3 cross a 3 bar. So the 3 looked like this in the weight diagram, and the 3 bar looked like minus that in the weight diagram. So what we do is we take one of the weights on the left-hand side and add each of the 3 weights separately on the right-hand side. So, for example, when we add this top right one and the bottom left one, we get a 0 weight. We'll take the top right one and add this bottom right one, I get a weight here. Okay, this is supposed to be a bit expanded actually. I should make it a bit bigger. So I get a weight here. And we do this one plus that one. I know we've done this one plus that one. Gives us one up here. Okay, so and then we do this for each of the weights on the left-hand diagram, and we end up with the following: a larger hexagon And we end up with 3 zero weights. Now, the hexagon, well, not a larger, it's a hexagon that's larger than each triangle before. So this hexagon with 2 zero weights in the middle was the adjoint representation that 8. And there's an additional 0 weight which is on its own, and that's the singlet representation. So a direct sum, just the weights are just there layered on top of each other with extra multiplicities. All right, good. So let's give you an important explicit example of the three-dimensional, well, it's of the fundamental representation of SU3. And these are named, these are in a particular normalization and basis. And when they're in this normalization and basis, they're called after their discoverer, the Nobel Prize winner, Murray Gell-Mann. So there are 8 of these matrices, and because they're in three-dimensional rep, they're 3 by 3. They look like this. And this is the conventional basis for the Gell-Mann matrices. Now, these don't correspond, as we'll point out in a second, these don't correspond to mathematics conventions. They're in the physics conventions, that's why I've written little t's. Now, so we've got some things to notice, that they're in physics conventions. In other words, they're Hermitian rather than anti-Hermitian. So T3 and T8 are in the Cartan subalgebra. In fact, they are they are a basis for the Cartan subalgebra. Or a basis. But the rest are not in the Cartan-Weil basis. They are in an adapted basis. With kappa AB is +1/2. You get the plus because of the physics conventions. The normalization's been chosen to give us a +1/2 here. Delta AB. That's quite normal for physics conventions, actually. And so because they're in an adapted basis and they're in physics conventions, the Lie algebra between them reads TA, TB is I, F, ABC, TC. With FI, ABC totally anti-symmetric. Okay, that's good. So this ends our discussion of the chapter of roots and weights. Next time we begin a new chapter, it's a short chapter, but we apply this to hadronic physics and explain some details of the hadronic spectrum by using this group theory.